So that's it. Let's go over one more time. We import our packages as we usually do, this time using Keras and importing some functions that we're going to use to create our model, to train and evaluate our model. We will load previously saved vector of labels and audio features. So we are loading the labels. We're encoding the labels using scikit-learn, going from strings, so the names of instruments, to integers. We are loading our MFCC feature vector. We're splitting our audio samples into a training set and a test set. Then we are using one hot encoding, so we go from integers to ones and zeros. Then we convert our shapes, we reshape our vectors to be according to definitions of Keras. That's what we're doing here. Always good to check your shapes. Then we are creating a fully connected deep neural networks model. We give this model an input. We tell what's the size, the number of elements in our feature vector. We are creating here a fully connected layer with 12 hidden units using a relu as an activation function. Then I'm creating a layer with 10 hidden units, another one with 8, and another one with 6 hidden units. And finally, I'm using a softmax activation as the output layer, and we define our model passing its input and its output. And with summary, we can see in text form how our model is looking like. Input layer 1, 2, 3, fully connected layer with relu, and one last layer with the softmax activation. We can also see our model as a graph. So we use the plot model function, and here we can see inputs and outputs of each layer and how our model is defined. Once we define our model, we can compile our model, and at this point we pass which loss function we are going to use, which optimizer, what kind of metrics is going to be used to evaluate the model during a test, during the training phase. Then we train a model, we define the batch size, the number of epochs, and we use the model fit to train our model. So our model here is going to be trained. Then we can also see graphic of the training loss and the training accuracy, number of epochs, and here is the value of loss and accuracy. We can also make the predictions, so we predict, we give the test set, we predict the model when we have predictions. We go here also, predictions will give us a number as a float, and we need to round it up so it will go to an integer that will be our classes. And here we use the inverse of the label encoder that goes from the integers to the names of the instruments. Then we can evaluate our model doing the same how we did before with other algorithms. We can also plot a confusion matrix and see what was correctly predicted and what was what were the mistakes. We find which were the files that were wrongly predicted. We can also see plot the history of our training. So this time we're plotting not only the training but also the validation, like with the test. So our predictions, and we can see, for example, our model, it's predicting 100% with accuracy of 100% our training, but the test, it makes 5 mistakes. And by looking at this graphics, you can see, you can have an intuition and see if you're training your model for too long, if you are having an overfit, or can try to have some insights to fine-tune your hyperparameters or define different network architectures, or also to see if you need to use different features. You can also use deep learning to extract features and not use predefined engineered features. Well, that's it. And next time we're going to use the same we're going to use also fully connected layers, but we're going to use grid search and try to fine-tune our parameters, try to improve our model, or at least to optimize it. Maybe we don't need so many parameters to train. Maybe we can achieve the same results with less layers. Maybe a shallow network will do the job. Yeah, I check you later.